So you have any doubts from the previous classes?
Hello.
Yes. Siddharth.
Uh, Karthik, while proving this like reachability and controllability
Mm.
Gramians, like okay, so reachability and what is it? Sorry, reachability Gramian and reachability subspace
Yeah.
that they are same.
Yeah.
So we tried proving that X into eta transpose is null space. So like basically, I was thinking that whether there are other ways of proving the same thing.
Mm. Proving.
Like the proof went like that.
Uh,
First, we tried to prove that okay, this is not in if something there is in null space. Then,
so you mean
or
this is the same as image of C,
yes, yes.
or is the same as C? Is that what you mean? Or in linear time, in continuous time case, linear time invariant system, it's all the same. Is that what you mean? This one, Siddhant?
Image of yes, yes, yes.
Oh,
No, no, no. The first proof,
uh,
the theorem
can you?
7.1,
Oh, I
like
don't have that.
reachability.
Yeah. So what is the
Re-
exact
okay,
thing we are trying to
reachability.
prove? Yeah.
So the reachable subspace is equal to image of reachability Gramian.
So
Like
reachable
image of
subspace.
WRT is image of
Oh,
WRT0.
okay. So basically, we have to prove that in this case is a subset of image of and uh, image of, because both are sets, right? So a set is equal only when these, uh, you know, so something like this. So you pick a vector from here, or in this case, so pick a vector from here, show that it belongs to this one. Also in the other case, also pick a vector from here, show that it belongs to this reachable. So that's what you mean, right? Because it's a set.
Yes, but
Yeah.
like so the image of WR and we showed that okay
Hmm.
that some if something is in kernel of WR.
Kernel of WR. Yeah.
Okay,
Yeah.
so X. Uh, so when we get a dot product of X1, which is in a reachable subspace, and eta 1, then it will be 0.
Yes. X1 transpose eta 1 is 0. Yeah.
Okay,
Okay. Both of
so
them look the same. Okay. Yeah.
uh, so can we prove that something like that certain state is not definitely not achievable in this reachable subspace? Like
Uh,
something is in kernel of something is in kernel of WR, and that is
yeah.
not certainly
Yeah.
achievable.
Correct. Because so we can say, so why are we doing this? So because image of this is equal to the orthogonal complement of kernel, right?
Hmm.
So that's why we take a vector in kernel, because it's easier to prove it that way.
Mhm. So is it
So
mean that if dot product of certain vectors
mm,
with X transpose
yeah.
reachable subspace is equal to 0, that space that state is not reachable?
Yes, you can't reach that space, right? Because if anything is in the kernel, it will always remain in
Hmm.
that 0 point, right? So reachability means
Hmm.
from the origin to some point. So basically, if you take any vector in the null space and you
Mm-hmm.
multiply it with WR, it will still be in
Mm-hmm.
at the origin, right?
Mm-hmm.
So it doesn't affect your state at all. So if it will just remain at the origin.
Mm-hmm.
So that's why.
Okay. So,
Yes.
mm,
So any vector in the kernel of WR, if you you know the basically kernel, the by definition WR times eta 1 is 0, right?
mm-hmm.
So nothing, I mean, you can't basically take that state to any other, you know.
Okay. Okay.
So yeah.
But the main thing was if anything is in my reachable subspace
mm,
and any other states, other vector is there, if
mm,
I do the dot product and that dot product like x transpose, suppose some other vector y1, so
mm,
x transpose y1 is equal to 0, then we
mm.
will say that okay, that y1 is not reachable at all.
Actually here, uh, okay, so basically your reachable subspace is the image of WR, correct? And you are seeing that it does not belong to the image of WR.
Hmm.
A vector which does not belong to
Hmm.
the image of WR, correct?
Hmm.
So this image of
Yes.
WR, if it does not belong to image
Hmm.
of
Yes.
WR, then you can't find a control law. I think it was phi transpose B transpose eta, something like
Hmm.
that, right? The control law. Yeah, B transpose phi
Hmm.
transpose
Yes.
eta.
Yes. Correct.
The other way, B transpose
Beta.
phi transpose eta 1. You can't find an eta 1 which will
Hmm.
take, or this
Hmm.
is U. You can't find a U which will
Hmm.
take your X
Hmm.
to your desired position uh, during the time interval T0 to T1.
Okay.
Correct? So that's all it
Yeah.
means. So you're saying now if the thing belongs to the kernel,
Hmm.
correct? So if it belongs to the kernel, so
Yes.
whatever eta 1 you find, it will be 0, right? I mean, so
Yes.
yeah, so if
Yes.
it,
Yes.
so you can't actually move any.
Yeah, I was just thinking whether there is, so whether there was like any other type proof we can think of, which will give
mm,
me
mm,
the solution that okay,
mm,
instead of x1 dot eta 1 transpose,
mm.
are there any other ways to prove the that theorem that R
Okay,
is equal to image of WR? Okay, thanks.
okay, okay. So I'll just erase this and we'll begin from scratch. So delete, delete. Yeah. Mm, okay, so we'll start off with today's lecture on controllability. Okay. So I'll just start off from the your under what we have studied in undergrad level. So in the earlier lecture, I had given only for x dot equal to ax. We had analyzed what is x dot equal to ax, its stability and all. Now we add a term bu. Okay. So now this system is it's not autonomous. So you have a external input coming in. So we are seeing if this external input actually can affect all the states, independently, and we can drive the state from say x naught to any other state x1 in finite time t0 t1. So that's basically the definition of controllability, right? What we learned in undergrad. So now we'll let's so we have only seen what controllability is. So there is something else called the reachability also, right? It sounds the same, but so I'll just write it down. So controllability. Okay, I'll start off with reachability. So reachability means there exists a input u such that we can take any point from the origin, say, origin to any point x1 belonging to Rn in time say t1 minus t naught. So at t naught you are at the origin, so I can draw a picture. So and you reach some point x1. No, this is your Rn in finite time t0 t1 minus t0, right? So that's the time interval. And in case of controllability, it's the other way. So it will be the same. There exists a u such that we can take any state in Rn to the origin in time t1 minus t0. So it's the other way. So in LTI case, both are the same. So linear time, so you have this. And we also define something called the controllable subspace and the reachable subspace. So the reachable subspace is the set of all x belong to Rn. So there is a, so I can write this as such that there exists a u such that x equal to t0 to t1 phi of t t1 comma tau v of tau q of tau t tau. Okay, so this is basically okay. This how did we get this? Can someone unmute? Like, why is it this expression for reachability? Can someone
It is taken from 0 to that point.
0 to, yeah, so
That is,
yeah, initial
x0 will
conditions
be
is
0.
0, right?
Yeah.
So initial conditions is 0, which implies this e raised to at x naught, or in this case, okay, phi. What is x of t? Is phi of t comma t naught x naught plus this entire convolution integral, right? So this integral term. So x naught is 0, correct? Because of the definition. So x naught is 0 from the origin you are taking. So you don't have this term. So this term goes to 0. Okay. I'll just erase this for ambiguity. Okay. So this is the set of all x's you can reach in finite time with the given input u. So this is the entire subspace. So you can just, it's a subspace by the way, so it will contain the origin. Basically you have to put u as 0, then you'll stay at the origin. So say this is the reachable subspace. If the dimension of the reachable subspace is 2, in this case, if this is R2, then we call it, we can reach any state in the subspace. Any reach in the any state in the state space. Similarly, you have the notion of a controllable subspace. So it is x belonging to Rn such that there exists a u, uh, so that we can write 0 equal to phi of t naught comma t1 x naught plus t0 to t1 phi of t1 comma tau b of tau. I think we should use another laptop. Okay, b of tau, u of tau, t tau. Okay. Mm, yeah, so this is obvious, right? From, you are basically taking any initial state x naught and all such initial conditions such that you can reach the origin. So that is controllability, right? So that's why I put 0 here. So these are two subspaces. Okay. So again, this will be some other subspace. So basically, any point here can reach the origin in finite time using input u. So these are the two definitions. So we'll look at a problem example where, in your classical control theory, what we used to do, like say A is 1 1 0 1 and B is 1 0. So this is in R2. So can someone say if it is controllable? or okay, in LTI case controllability implies reachability, so it's the same. That's why we didn't distinguish between controllability and reachability when we learned it in undergrad. So now can someone say if it is, so if it's controllable? So how do you usually check for controllability? I mean, the easiest way you used to check. So I mean, you can unmute and say.
A B, A square B having full rank.
Yeah. So AB is 1 0. So that is
1,
1 and 0 0. Okay.
0.
Yeah. So is this controllable?
No,
Yeah. So it is not controllable. Why?
that is singular. That rank is 1.
Rank of this controllability matrix, right? I'll call this C is equal to 1. Correct. So we'll just look at the what is happening, in the state space. So if you have this as R2 with x1 and x2, so I'm saying that there is a span, right? There is a direction, or there is a subspace. Okay, what is that subspace? Okay, can anyone guess the subspace from this? Hello, can anyone guess the subspace? You can unmute and say controllable or the reachable subspace from this
It's a line passing through the origin.
line. So I mean, you can exactly pinpoint which line it is. Yeah, it's a line because rank of C is 1. So, in 2 dimensions, any subspace with dimension 1 will be a line. And in, so you can actually
X is
pinpoint the
equal to
line.
Y. X is equal to Y.
X is equal to Y, or is
I
it,
mean, X1 is equal to X2.
mm, shouldn't it be the X axis?
X-axis.
Yeah, it will be the X1 axis
Ah, yes,
because
okay. Yes, yes.
this, right? So 1 0. So it will be the X1 axis. So this entire space. So basically, if you are in the origin, you can only go to 1 0, or 2 0 3 0 minus, along the span. And if you are only on the, okay, someone is here. So if you are somewhere here, you can go to the origin. But if you are somewhere here, you can never go to the origin. So that's what it means. Okay. Yeah. Cool. So this is the reachable and the controllable subspace. Now, so yeah, we'll just look at, this was for a continuous time case. So I'm just taking the same matrix for a discrete time case. So let's check. Okay, so x of k plus 1 is the same a x of k plus b u of k. Okay, so I'll just write down what's happening, because in discrete time case you can actually get to the origin, or any state you want from any initial conditions in at most n steps. Okay, so uh, okay, so that's called n step control. So I'm just doing this for the continuous and the discrete time before moving on to the Gramians. So, and we'll see what Gramians are actually. So for the discrete time case, say I'm taking the same a. Okay, a is 1 1 0. Okay, before that I'll just say what's happening as a, in actuator, what the actuator is doing. So you have x1 dot is x1 plus x2 plus u, right? If you expand this as equations, and x2 dot is x2. So what the actuator is actually doing is, it is capable of controlling this x1 dot, correct? Because it's directly entering the dynamics of x1 dot. So basically you can use this, say this is a motor or something, u is your voltage input or anything, and it's directly controlling x1. but x2 has nothing to control. It's just evolving on its own, correct? So u is not at all affecting this x2. So that's why you see here you can only move along this x1 direct. You know, this x1 the x1 axis is the only controllable subspace. So that's the physical reason why it's, you have to stick on to this 1 0 subspace. Okay, I hope it's clear. Okay, yeah. So that's the physical meaning. The actuator is incapable of controlling the second state. Okay, now we look at some n step control. So if I take x1, what is x of 1? A x of 0 plus b u of 0, correct? What is x2? A x1 plus b u1, which is same as mm, a square times x naught. So I'm just substituting here, plus ab u of 0 plus b u of 1. So for, and this will go on. Okay, so just for simplicity, let's look at okay. mm, okay, just a second, I'll just take up an example. Yeah. Okay, so we'll first look at a simple case of, a scalar system before moving on to this A. So x of k plus 1, or it's a scalar, okay, x belongs to R, is equal to x of k plus some b times or some u of k. So this system is trivially controllable because the matrix is only B. It's a scalar value and it has to be non-zero, and it is non-zero here. That's all. So it is controllable. So what is happening is, here what is n? N is equal to 1. Okay. So here what I'm saying is, from any initial conditions x naught, I can take you to any, say, in any x at k equal to 1, in the entire state space. So let's say I am at x naught equal to 1 and I want x1 equal to 100. Can I do that? So is it possible? In just one step I can reach anywhere in the state space. I mean, someone can unmute and say if it is possible. I mean, you can just look at this equation. U is in our control. So by the way, so is it because it's not clear? I mean, you can just unmute and tell if it's not clear. Uh, Soumya, is it clear, or do you have to explain more?
Yeah, it is clear. My intuition is it is possible if the u is very. I mean, accordingly, if we give a
What?
input u,
Yeah, what will be u of 0? It's, you can find, right?
yeah, it is possible.
So what is u of 0?
99.
Yeah, that's all. So so we are not saying about the physical limitations, like I can't give us 100 volts or 1000 volts to the system. I'm just saying that I can take. So it doesn't, controllability doesn't care about the physical constraints. Controllability only says I can take if you give me this much fuel or this much voltage. So of course, like, so this will be an example. So yeah, so this is okay. I hope this is clear in the one-dimensional case. Now let's look at the same example in the two-dimensional case. Okay, so x of k plus 1, here x belongs to R2, is equal to 1101 x of k, okay, plus 10 u of k. So let's look at the first step. What is x of 1? It is a x of 0 plus this 10 u of 0, correct? and what is x of 2. So I am guaranteeing that I can reach at most n step if the system is controllable. Now we have shown that the system is not controllable. So here n equal to 2, x of 2 is a square x naught plus uh, b u, okay, this is, okay, this will be u1 plus ab is again 1 0, right? We have found it's 1 0 here. B and AB are the same, so it is 1 0 u naught. Assume for simplicity, I'm starting from x naught equal to 0. Okay, just so that it's easier to understand. So so x of 2 will be a linear combination of these two vectors, correct? Which is same as 1 0 u1 plus u0. Okay. So now you can see why I can't go to any state even in 2 steps. Do you think I can go in 3 steps? Someone can unmute. Arjun,
Actually, I didn't get that. Why? What should be inferred from this equation?
which equation?
I mean, this last one.
Yeah, so the last one, so basically what is x of 2? It's a vector. Is a linear combination of 1 0. So it's a linear combination of 2 other vectors. But the problem here is that those 2 vectors are linearly dependent, right? They are dependent vectors. Correct? So this will be,
Yes.
in general case, this will be B, this will be AB, correct?
Yes.
Here the problem is it's not controllable. So B is equal to AB. B and AB lie on the same line or the same span.
Okay.
So they are basically, it's not a linear combination, it's a dependent, these two are dependent. So you can only stick to this line 1 0. Okay.
Yes. Yes.
So let me just, for a change, I'll take the A as same 1 1 0. So this is nothing but a line, right? I mean, it's the same, this axis, right? Whatever u1 and u0 you give, you will always be in this line, correct? You can't move out of that line. So now let's take a equal to this and b equal to say 1 1. Now let's see what happens. Is it controllable? B, what is AB? 1 plus 1 2 and 0 plus 1 1. So this has rank 2, correct? So we can actually, I'll just do the same steps again and show you why it is controllable and why you can reach anywhere in 2 steps. So x of 1 will be equal to ax naught plus, what is b? B was 1 1 u naught. X of 2 is a x of 1 plus 1 1 u 0, which is same as a square x of 0 plus ab was 2 1 u of 1 and 1 1 u of 0, correct? So I again assume x of 0 is 0. It doesn't matter. So wherever you are, you can always change that. And so x of 2 is a linear combination of 2 1 u1 plus 1 1 u0. Now u1 and u0 is in our hands, right? So I can take u0 as 5 and u1 as minus 2. It doesn't matter. So what we are saying is x2 is a linear combination of 2 linearly independent vectors, which means it can span the entire space, right? Rn. Physically, it means using appropriate u1 and u0, I can take any, from the origin or any point to any other point in the space, correct? Because it's spanned by 2 linearly independent vectors. So now, is it clear? Soumya, is it clear?
Yes, it's clear.
Yeah, so that's the physical interpretation. Like, so you just need at most 2 steps, right? In this case.
Yes.
But then I'm saying I can go to certain uh, certain points in space in 1 step also. So the trick here is, if I'm lying on, say, the span of 1 1, I can reach it in one step, right? Because I just need u naught, correct? So I can just reach anywhere in the span of 1 1 in just one step. I don't need u1. I can set u1 and all the other control to 0, correct? So can be reached in one step. It's easy to visualize. So if I take x of 2, so okay, before that, x of 1 is ax naught, which is 0, times 1 1 u naught, right? So that's where this all this what we learned in linear algebra comes, the span, the basis, all these things. So this is basically same as span of 1 1, and I just use one step control, right? Is it clear? So yeah, any doubts here? We'll move on to Gramians and stuff if you don't have any doubts. So this is all this is quite intuitive to understand. Now in the lectures, so you encountered something called the Gramians,
Now,
or
is
yeah,
this applicable for all controllable or I mean all state spaces that are controllable? I mean, with just one
systems.
step. Yeah.
Yes. So there are certain directions in which so if the system is controllable, okay,
Ah,
okay. So if the system is controllable, you can reach the
in,
entire space in at most n steps. It's at most n steps. Certain
okay.
states can be reached even in less than n steps. Okay.
Okay. Okay.
But if the system is not controllable, then certain um, states can never be reached even if you go beyond n steps.
Okay.
So I hope you got the idea. This is for discrete time, okay? The steps always is in discrete, not continuous time. So yeah. Okay, let's look at Gramians. So we define these quantities called the reachability Gramian. It's an integral t0 to t1. So phi of t1 comma tau p of tau b transpose of tau phi transpose of t1 comma tau t tau. And same way, so I'll just copy, okay, I'll just write it down again. The controllability Gramian is t0 to t1 phi of t naught comma tau. You can see that it's interchange, right? T1 and t tau. That's because we saw this figure, right? One is going from the origin to any point, the other one is from that point it's coming to the origin. Okay, so that's why it's reversed. It's not tau, b of tau b transpose of tau phi transpose of t naught comma tau t tau. Okay, so this is so there is similarly there is something called the observability Gramian also that we'll see later. So in the next lecture, I feel. So this quantity actually gives a lot of information about which all directions are controllable and which all directions are easily controllable, and it actually gives how much energy we need to spend to reach that state. So so here, the what does this condition say, the rank? It just says that it's controllable, and the number of the dimension of the reachable or the controllable subspace. But this Gramians encode the energy information also, like how much energy, or how easily it is the state is reachable or controllable. So we'll look at an example. Uh, so yes, yeah, we'll look at the same. I don't want to change this matrix because it's easier. And b equal to 1 0. So we have shown that it's not controllable, right? So okay, before that, for those who have not watched the lectures, I'll just say one more thing. The controllability subspace is the same as reachable subspace is the same as image of this. Okay, I need to change this. Okay, I'll call it just C for now. Okay, this is C. I'll just call it C for now. Okay, image of C is the same as image of WR is the same as image of WC in linear time invariant cases. Okay, so we have seen this. I think this part is clear for everyone why it's so. We just showed that, this 1 1 and all. So I hope this part is clear. We'll look at what this part means. Okay, so this is a matrix, right? This is an n cross n matrix. WR and WC are n cross n matrices, correct? Because e raised to a t, b transpose, e raised to a transpose t. So these are matrices again. So image of a matrix, it's the same, I mean, which you have studied. So image of a matrix. So we show that this in the lectures that this equivalency holds. So if you want, you can watch the lectures, if you want. We won't cover that proof here. We'll just look at an example. Okay. So A is 1 1 0 1 and B is 1 0. Okay. Yeah. So we'll first find e raised to at. Okay. So I mean, if you want, you can calculate right now, but I have found it beforehand. So it's e raised to minus t. T e raised to minus t. I mean, actually looking at the matrix itself, you can find it out. It's 0 e raised to minus t. Okay. So and now we have, what is WR? So this is a continuous time LTI case. So WR will be, let's say T0 to T1. I'll plug in the values later. E raised to, so in the continuous time case, phi T1 T tau is e raised to 8t T1 minus tau B of tau B transpose of tau. Okay, so this is again LTI case, so it will be B transpose. There is no parameter. E raised to A transpose T1 minus tau D tau. So you can compute this huge matrix as, it's not huge matrix, it's a bit difficult to multiply, and you can use MATLAB. So I've just computed it. It's e raised to tau 0 0 0. I mean, you can immediately see that it's not controllable because there is a column of zeros, but I'll just write it down. It will be 2 minus 2 e raised to 2 t naught minus t1 0 0 0. Okay. Now I've said that the controllable subspace or the reachable subspace is equal to the image of this WR, correct? Which is image of this matrix. Let me plug in T0 equal to 0 and T1 equal to 1 just for ease, so that will be e raised to 2 times 2 e raised to 2 minus 2, correct? Yes. 0 0 0. So this is some constant number. I'll call it some A. Okay. Image of some A 0 0 0. Okay. So as we saw, previously also, what is the image of this? Same as a line, right? I'll draw it properly. One sec. What is the image of this? This is nothing but, again, this x-axis, correct? X1 and X2. Okay. Now you can find, for let's, in the other case, when I had taken B as, when A is 1 1 0 1 and B as 1 1, you can again find this WR. It will be some A, B, C, D. Okay. Okay. Or I'll write it in a better way. W1, V1 and V2, where V1 and V2 belong to R2, are linearly independent. Okay. So is there any doubt here in what we did? So any doubts regarding the computation of the Gramian? I'll tell you the physical meaning a bit. What the in the computation part, does anyone has any doubt as of now? Okay. So now we'll look at what the Gramian actually represents. Okay. So can someone say what the property of this matrix? Property of WR. Someone can unmute and go back to the linear algebra class, or you can just refresh and just say what this WR, what the property of WR is. You can immediately see from the matrix multiplication. Siddhant,
Sorry, I'm not able to recall.
Soumya, you are saying something.
Is it positive definite?
Positive definite. Okay,
No,
that's
semi-definite.
firstly, is it symmetric?
I am not able to guess it.
I mean, it is symmetric. So
Okay.
yeah, so positive definiteness. Okay, that I'll have to check if it is always positive definite. I think it is positive definite. I am pretty sure it is positive definite. Okay, so omega r is something like x transpose, right? So you can always write like this. So this is a symmetric matrix, and yeah, I think it should be positive definite. Yes, yeah, correct. It should be positive definite or positive semi-definite. I'll check and say. But yes, the eigenvalues will be at least non-zero for sure. Okay, so now in the controllable case, so WR is symmetric. Okay, and eigenvalues will always be greater than or equal to. Okay, I'm not commenting on that right now. So I have some eigenvalues. What is the other property? They are real, right? Because it's symmetric. Also, the eigenvector are orthogonal, correct? Because WR is symmetric, you can always find eigenvectors that are orthogonal. Okay, so what does this mean? So for in the second case, when a equal to 1101 and b equal to 1 1, I found the eigenvector. So in this case, the first case, you can find that the eigenvalue is this a, right? And the other eigenvalue is 0. So it is positive semi-definite. Okay, got it. Yeah, so it's positive semi-definite. So a here is non-zero, and here it is 0. Those are the eigenvalues, correct? So let's say I have lambda 1 and lambda 2. So I have just decomposed the system. I can always find a diagonal form. Why? Because it's a symmetric matrix. So the d WR is something like this. So what it actually represents is, in this case, I actually computed the eigenvalues 0, 0, and some 4.6. Okay, you can actually find the WR, then find its eigenvalues. It will be this. Okay, this is the diagonal form. So what this says is, so if I take this as lambda 2 and this as lambda 1, it says that I need energy to go. So I'll take lambda 1 v1 and lambda 2 v2 as the eigenvalue eigenvector pair to go in the direction of v2 is less than energy to go in the direction of, oh, one sec, it's the other way. Sorry, I took lambda 1 as the reverse. Okay, so we have lambda 1 is greater than lambda 2, correct? which implies this in this direction, whatever you give the energy, it will be amplified because these eigenvalues are scaling terms, right? We saw in the eigenvalue decomposition, these are scaling terms. So along V2, whatever energy you give, the input you give, it will be 4.6 times the, as the output. So you just need very less energy to go along this direction. Okay. So what this Gramian actually does is, it takes a circle, a unit circle. Say this is your total fuel you have, and this is transforms into some ellipse where this is your lambda. Let me check. This is lambda 2 direction, and this is lambda 1 direction. Okay. So did you get the physical meaning of what's happening? So this is in R2. So as you can see here, this the fuel needed to go in the lambda 1 direction is much lesser, right? Is it clear why it's much lesser? Because with the same fuel, so fuel is the same, right? It's a unit circle. With the same fuel, I can go in this direction, the length of this. So if I take this is as 1, this will be lambda 1 times 1, right? This direction. So I can go farther in this direction rather than this direction. Okay. So is it clear? Do you have any doubts about the Gramian, the physical? So the proofs and all are in the lectures. I'm just giving you a physical intuition what's happening. So you can actually choose according to the fuel you have, fuel or the battery store, the mAh left. You can actually control, using the Gramian tells you which directions are easier to control. Okay. So is it clear, or do you have any doubts? Okay, if not, we can go to the next one. So now we have to check for controllability, right? So we have just given what is controllability, and we saw one condition, the rank of C matrix to be, rank of the controllability matrix to be full. So we have some other tests. So the one of the first test is called the PBH test. It stands for the names of three scientists. So it's PBH test. So it says controllable. So we always write the pair AB as controllable. Like this. If and only if rank of A minus lambda I B, this is a it's a concatenated matrix, or so is equal to n for all lambda equal to the eigenvalue of A. So this is one of the other tests which you can use uh, for testing if A and B are controllable. We'll use some other example. Let A is 2, 1, 0, 3 and B is 1, 0. So what does this say? What are the eigenvalues of A? 2 and 3. Okay. So what is this matrix? A minus. So I'll check for lambda equal to 2 first. For lambda equal to 2, what does this give? 2, 0, 1, 0, 1. Correct? Is it correct? Yes. And B is 1, 0. Is this correct? Yes. Right. Yeah. So what is the rank of this matrix? Is 2. Which means in this direction, so when lambda equal to 2, along that eigenvector, I'm safe. Now let's look at lambda equal to 3 and see what happens. So what is A minus lambda I? 1. So it's minus 1, 1, 0, 0. And the other vector is B is 1, 0. So I'm just basically writing this with respect to lambda equal to 3. So what is the rank of this? Is 1, right? Is it 1 or is it 2? What's the rank of this matrix?
1 only.
Yeah, so it's 1. So which means this doesn't pass the rank condition, correct? So you can see actually what's happening here also. So mm, so this has failed one of these conditions, right? So for all, so it says for all lambda, not for at least one lambda or two lambda. For all lambda, this should have a rank of n. So here it doesn't hold. So which means it's not controllable. Now I'll give you a small special case. So it will actually tell you how many inputs we need. You know, U1, U2, U3. It's a multi-input system, right? It can be a multi-input. So in the case when you have repeated eigenvalues, okay, 0, 0. What do you think rank of A minus lambda I B would be? So we'll just check this out. 0, correct? Lambda is 1, so it will be 0 in both the cases, and B will be, I'll take the same B. So this will never be, controllable, right? In not even in one direction, right? So this, for all lambda, we can never find B such that this has rank 2. Here at least this has rank 2, correct? But here you can never do that because the eigenvalues are repeating. So rank is equal to 2. So this tells you that one input is not sufficient. You need to add one more input, which means the B matrix, say, is now 1 0 0 1 U1, or I'll just change this to 2 just for, so this is your B and this is U, so this is U2. So what happens now? Same matrix, if I write, this is 0 0 0 0 1 0 0 2. This has a rank 2, correct? So this test actually tells you not only that if it's controllable or not, it tells you uh, it also tells you if one input is sufficient or you need more inputs. Okay, so is it clear? Any doubts? Okay, so we'll move on to another test. So the second test is called the eigenvector test. Okay, so it says a comma b is controllable when eigenvector of A transpose is not in the kernel of B transpose. Okay, so this is another condition which you can check. So all eigenvectors of A transpose should not be in the kernel of B transpose, then it is completely controllable. So we'll look at the same example. So it is 2. Okay, should I change the example? Okay, so let's first check what is the kernel of B. So B is 1 0. What is the kernel? Set of all vectors x such that this B transpose x is 0, right? Or x transpose B, doesn't matter. So this is 1 0 times, so x will be 0 1, correct? So the kernel of B transpose is span of 0 1. Okay, now let's check what are the eigenvectors of A transpose. What is A transpose? From the earlier thing, so it will be 2 0 1 3. So the eigenvectors are, for the lambda equal to 2, the eigenvector was 1 minus 1. You can check, so if you just subtract and You can check that the eigenvector will be 0 1. So now you know why the system is not controllable, because one of the eigenvectors is the same. Okay, so that's the reason why this. So I mean, all the tests are equivalent. So yeah, so this is another test, which means a comma b, the pair a comma b is not controllable. So what do you do if it is not controllable? So I have shown that it's just not controllable. The system is not controllable. You can't steer the system to any point in the space using my control. So what do we actually do? Any suggestions, or Soumya?
We'll find something that is closest to our point.
Closest to, okay. But mm, okay, yeah, I understand that. But uh, okay, that's a good practical way of thinking. Yeah. So we just find which is the nearest way, nearest point in the controllable subspace and go to that. But say, mm, say I'm here and I can only go along this, in this space, and where I want to actually reach is here. So the nearest point would be here, right? Yeah, that's actually a good thought. Like I've never thought about that. Like the nearest point. Nice. Okay. So what is the, that's a really good point. Uh, will so yeah, there is, so basically the other point would be change the control structure itself, right? Add actuators, which is more costly, or you know, actually his point is really good, so I can't counter that. Okay, so yeah, so we look at some other concept of stabilizability when the system is not completely controllable. Stabilizability. So in stabilizability, what we do is we take the entire system, say this is the A matrix, and we partition into two using similarity transforms. So you can always find a T such that A bar is T inverse AT, which is equal to A controllable sum A1 to 0, A uncontrollable. So which means the system has been partitioned, right, into two blocks, which is controllable and the other one is uncontrollable. Similarly, B also can be changed to B, C and 0. So you can actually see that when you write x bar equal to A bar x bar dot, okay, plus B bar U, this is AC A1 to 0 AU x bar plus BC 0 U. So you can actually see that this input only enters this section, correct? It does not enter this section because it's 0. So what actually you can say is, if this is the controllable part and this is the uncontrollable part, the input enters here and this will be 0. So the next best thing to do is I can control some states in the system, okay? Uh, but what about the other states which I can't control? I just have to hope that they are stable. Okay, so let's say I have a state space here, x1 and x2. Okay, now I am saying that all the states which lie on this line, I can take it to the origin. Okay, so what I'm saying is whatever is here, I can always take to the origin. I'm guaranteeing that. It's not completely controllable. You can see that the span is just a one dimensional line in the R2 plane. So what I'm saying is I can take this, but what about the other in the other direction, say along this direction? So if I can, by luck or some chance, some probability, you if I can get a system in this direction, if it is automatically going to the origin, then I don't have to worry about it, right? So one of the states, I can guarantee that I can take it to the origin along this line. The other state, or in the along the either direction, if it blows up, then I'm done. I can't do anything. I'll have to add actuators. You know. So the problem is the uncontrollable states have to be stable. That's called stabilizability. Okay. So that's what stabilizability means. You have similar tests for all these things. You can go through lectures for that. The tests are similar, just that you have to take the okay, for example, in the PBH test, we have taken for all lambda, right? We just have to check if the uh, mm, we just have to check if the positive eigenvalues are uh, are controllable, correct? So we just have to check for eigenvalues of a with real part greater than 0, not for all lambda. So they have to be controllable. That's all. In this case, in the eigenvector case, this eigenvector of A transpose corresponding to the eigenvalue which have positive real part should not be in the kernel of B transpose. Okay, so that's a small modification. Yeah, so that's all in this session. So if you have any doubts regarding whatever is taught, so I hope you understood what the Gramian physically means. It's actually the amount of energy required to go in one direction compared to the other direction. Okay. So any other doubts? Okay. If not, then we can wind up. Yeah. Okay. Thank you.